Electrostatics, Electrostatic Fields, Series on Electromagnetic Field Theory, lecture number 1.11. Electric field intensity is an important property of electric fields. Electric fields are regions surrounding charge distributions. If the charge distribution is stationary, the field is called electrostatic field. When a charge is placed in electric field, it experiences certain amount of force. If this charge happens to be a unit positive charge plus 1 coulomb, then the force experienced is field intensity. Now, in the present session, we explore electric field intensity. We try to derive expressions for electric field intensity in the fields created by different charge distributions. First, let us define field intensity. Electrostatic field intensity at a point in the field can be defined as the force exerted by the field on a unit positive charge placed at the point. It is indicated by capital E. Units are volts per meter. Coulomb's law. Using Coulomb's law, it is possible to find field intensity due to a point charge. F force, Coulomb's law. Force between two point charges is 1 by 4 pi epsilon capital Q small q by r square r cap. What it says is, let us suppose there is some point charge somewhere here. Small charge, small size of charge, point charge. Let us call it capital Q. Another charge is there, small q. Coulomb's law says the force between them is given by this form. The force experienced by charge Q when it is 1 coulomb becomes 1 by 4 pi epsilon capital Q by r square r cap. And this force by definition is field intensity. Therefore, E equal to force with Q equal to 1 coulomb, which is equal to 1 by 4 pi epsilon Q by r square r cap. Here, notice in this expression, we are moving from force concept to field concept. Force is something that happens in between two charges, whereas field is something that is associated with the charge distribution. If you consider a point charge, surrounding this charge, there is a region. It is not an ordinary region. It has certain special properties, certain special characteristics, features. It is something special. One of its special properties is intensity. Field intensity at a point in the field, it is the force experienced by the charge when it is plus 1 coulomb. Field obeys superposition principle because force obeys superposition principle. Field is force on a unit positive charge. Therefore, field also obeys superposition principle, and expression for a single point charge can be extended to other distributions also. We have seen in the previous slide, we considered a point charge capital Q. Field intensity at a point P is given by E, is here. At this point, it is given by 1 by 4 pi epsilon Q by r square. This is our distance, r, and unit vector is, let us say, r cap, r square, r cap. Let us suppose there are several charges as shown in this diagram. Instead of one, we have several charges. Q1, Q2, Q3, Q4, etc., Qn. The field intensity at the point P then becomes, according to superposition principle, it is field intensity at P due to Q1, field intensity at P due to Q2, plus field intensity at P due to Q3, plus due to Q4, etc., due to Xn also. So in case the charge distribution is group of point charges, then electric field intensity is E1 plus E2, etc., En. It becomes 1 by 4 pi epsilon Q1 by R1 square R1 cap plus Q2 by R2 square R cap R2 cap plus Qn by Rn square Rn cap. Of course, this lengthy expression can be put into a compact form using the symbol sigma 1 by 4 pi epsilon sigma k equal to 1 to n Qk by Rk square R prime Rk prime. Charges, they are available in two types of distributions, discrete and continuous. So far we considered field intensity due to a point charge, field intensity due to a set of point charges. Point charge, a group of point charges. These two fall in the category of discrete charge distribution. distributions. Continuous charge distributions are also in existence. Three types are there. One is line charge distribution. It is shown here. Line charge distribution. Another is surface charge distribution. Fourth one is volume charge distribution. Here we try to find out expressions for field intensity in the field due to line charge distribution, surface charge distribution, and volume charge distribution. For that, we need to know certain aspects of these three distributions together called continuous charge distributions. First, consider line charge distribution. Line charge distribution is one where the charge is in the form of a very thin line. Only length dimension is there as far as these charge distributions are concerned. When it comes to surface charge distribution, here charge is in the form of thin sheet. Length is there, breadth is also there, but no thickness as far as these charge distributions are concerned. When it comes to volume charge distribution shown in C, here you can find it is having length, it is having breadth, it is having thickness too. So volume is there. Volume is there as far as these distributions are concerned. As when it comes to line, only length. When it comes to surface area, when it comes to volume charge distributions, volume is charge in unit length of line charge distribution is indicated by lambda. It is called line charge density. Units are coulombs per meter. Charge per unit area in surface charge distributions, it is indicated by sigma. It is called surface charge density. Units are coulombs per meter square. When it comes to volume charge distributions, charge per unit volume, it is indicated by rho. Units are coulombs per meter cube. Now, let us again revisit line charge distribution. Let us consider a small length of line charge, dl, as shown here. Small length, dl, differential length. The length is so small that we can consider the charge within this length as a point charge. Dimension wise, it is very small. So the charge within this small length, it is actually becomes lambda dl. dl is there, differential length. Therefore, this charge is differential charge. The charge within length dl, it is called differential charge. It becomes equal to lambda dl. This dq can be considered as a point charge. Similarly, when come to surface charges, consider a small area, differential area. This area, differential area, is so small that the charge contained by this differential area can be considered as a point charge. This charge is sigma dA. As this charge is within a differential area, it can be considered as differential charge. So differential charge is sigma dA, and size wise it is small, so we can consider it as a point charge. dq is a point charge. Similarly, when we consider differential volume, it is so small, size wise, the charge within the differential volume can be considered as a point charge. This point charge usually indicated by dq, differential charge. Differential charge is rho d tau. Rho is charge per unit volume, d tau is volume. Therefore, charge within that volume becomes rho d tau. Point is dq rho d tau equal to rho d tau can be, it is so small that it is a point charge. So in all the cases, dq. Here dq is lambda dl. Here dq is sigma dA. Here dq is rho d tau. All these dqs are point charges. This is the aspect which is required to be kept in mind before going to deriving expressions for field intensities for this continuous charge distributions. Here are shown field intensity expressions, three expressions for the three charge distributions. First one is for line charge distribution. It is E equal to 1 by 4 pi epsilon integral lambda dl by r square r cap. E equal to 1 by 4 pi epsilon sigma dA r square r cap integration. Similarly, this is for volume charge distribution. Now we move further to derive these three expressions. For continuous charge distributions, to find expressions for fields, we consider expression for field intensity due to a point charge Q. This is the expression. Already we have derived it. Now differential calculus. dE becomes dQ. Now E becomes integral dE 1 by 4 pi epsilon integral dQ by square r cap. But in case of line charge, dq is lambda dl. We have seen already. Therefore, E equal to 1 by 4 pi epsilon dq by r square r cap becomes 1 by 4 pi epsilon. In case of dq, I can replace lambda dl. So this is the expression for line charge distribution. In case of surface charge distribution, dq becomes sigma dA. So this is the expression for surface charge distribution. In the third one, dq has been replaced by rho d tau, making the expression valid for volume charge distributions. All the expressions so far derived for field intensities, they are being shown in the form of a tree diagram. Notice in this diagram, field intensity due to a single point charge is given, due to several point charges, due to line charge, due to surface charge, due to volume charge. These two, they fall in the category of discrete charge distributions. Remaining three are continuous charge distributions. Now, let us see first expression. E field intensity R. What is this R? It is vector. Okay. It is position vector of the field. See, here is Q. Surrounding Q, field is there. In the field, we consider a point. At this point, what is E? This is the question. E at R. It means the position vector of point P is R. This is the position vector of the point P. This is R the same. It is 1 by 4 pi epsilon. Q, R cap is there. R cap is, R prime. R prime indicates position vector of capital Q. So, position vector of Q. What is R? Of course, R is the distance. The distance. What is R cap? It is unit vector along the vector from Q to field point P. So, in all the expressions, we can see field intensity is at R, whereas source distribution is at R prime. The same meaning everywhere in all these expressions, R prime, they carry the same meaning. So this is for a single point charge, whereas this is for several charges. This is for line charge, lambda, dl, r cap, r prime, dl prime. Here one more thing also required to be told. Instead of dl, dl prime is used. Prime indicates that integration is to be performed over source distribution. You have to perform integration over source. In these formulas, there is no scope for confusion, but when we encounter surface integrals or volume integrals, there is a possibility to arise some confusion. The region of integration, regarding the region of integration, where to integrate. To avoid that confusion, prime is used to indicate that integration is over source distribution. dl prime is integration is over the source. Here also, dA prime, d tau prime, integration is over the source distribution. Prime indicates integration over the source distribution. This is what I want to share with you regarding electric field intensity.